In this video we're going to introduce digital signals, discuss resolution and its effects on data rate. So let's start. Digital signals. Digital signals are a really important subclass of all discrete time signals. The independent variable remains the same. It is an integer, small n, but now the dependent variable, rather than coming from the real numbers, comes from a finite set of integers. So it is also discrete. So, instead of saying that x of n is a real number, we don't do this, we actually say that x of n takes on one of only some discrete set of values. In this case from, for example, the discrete values 0 up to d-1. And that means that the discrete time signals can only take a finite set of vertical values when you plot them in a stem plot. In this particular example, we can see that this might correspond to d equals 0, 1, 2, up to 7. So d equals 8 in this case. And why is this useful? Well, this is very useful, because once we have a discrete set of vertical independent variables that can be taken, we can think of representing each of these with a digital code. And the number of bits that we need is basically the logarithm of the number of levels. And so, that allows us to represent signal values down here. As for example, the digital code 000, 3 bits. There, signal value here is 1, again 3 bits. 001, and so on up to 1114, 7. And so, this allows us to convert a discrete time signal into basically a string of bits. That is exactly the kind of representation that we need if we're going to represent this signal in a digital computer, store it into memory, put it on a compact disk, etc. So these are called digital signals. And it turns out that this is again how signals are really computed with, and really stored. An example, in compact disks the number of bits used to represent one individual sample, a height above the time axis is 16 bits. Which means, we can represent it with a resolution basically of 1 Indiana 65000 different levels, which is a very fine quantization. And at this fine of a level of quantization, you can effectively model or think about these values as basically taking a real value. So, even though real signals in MATLAB and digital signal processors that are processed are digital, this assumption that they take real values is really quite reasonable. And it certainly simplifies all of the mathematics that one is going to do. Here, an example of digital signal is shown with d equal 4, x of n can have only 4 possible values and each value can be represented by 2 bits. The resolution is 1/4 or 0.25. Next, we have shown 2 digital signals approximating an analog signal. The one in blue has 8 levels which can be represented by 3 bits. This has a resolution of 1/8. The red signal has 16 bits with resolution of 1/65,536, which is very fine, and better approximate the analog signal. For the later case, it however take more memory, and also results in communication overburden of increased data rate. So to summarize, we talked about digital signals, effect of resolution and data rate. And we came to a very important conclusion that, when we increase the resolution we get a better form of the analog signal but will result in high data rate. Your support would be highly appreciated to like and subscribe to the channel.